Unit 2 is transformations. Now, depending, I don't know. My kids that are in 9th grade, have you guys heard of transformations? Did you do transformations?
Yeah, we did them. It was like, remember?
Was it in 7th grade?
No, it was in 8th grade in algebra. Remember, Lily?
Did you take shapes?
Like make the things, make the lines bigger and shorter.
Okay, so you probably did transformations with like parabolas.
Yeah,
Take
that's
a
what we were doing.
deep breaths. When you took a parabola and you slid it to the left or to the right or up or down, right? And then yes, you could open it up or make it narrow. Now, if you did 8th grade and 8th grade math, you also should have taken shapes and moved them to the left, moved them to the right, up, down, flip, rotate, things like that. Now you can flip your parabola, that's reflecting it, right? So these ideas actually are interconnected. It's not, if you've never transformed shapes before, you're gonna do it this week. And it's not difficult, so just take deep breaths. It's not difficult. And then mostly at this level, it's not about performance, like actually doing the transformations, it's more about interpreting them. Okay? But it is good to be able to do them first. Now, there are reasons why I love this unit. Can anybody read this name?
Martin.
Okay. Watch the mouth. Right? Martin Gardner. Thank you, Martin. I know it's like a weird cursive thing. Now I need to escape so I can actually manipulate it. But watch this thing. I'm going to escape. And then I'm going to do this. And I'm going to go 180 degrees. Did you guys see it turn? It's still Martin Gardner.
But it didn't even move.
It did. So focus on like this being the center point and not moving. So I'm just going to go like this and let it drop.
Oh, it's like the ambigram thing on YouTube.
I know, this is not as good as the other one. I might be able to animate it, but like it has symmetry that when you rotate it 180 degrees, it looks the same.
Yeah, it was on YouTube.
Okay.
When I was using it.
So now there's this one.
It's called the ambigram.
That one's boring.
So can you guys kind of see something that's kind of like a G, but then you see the Martin? Come on, buddy. This one.
Come on, buddy.
So now can you see like the Gardner?
Yes.
And it's a flip. It's a reflection. So Martin Gardner is a mathematician, but he's also did a lot of word art and puzzles. And what's really interesting about this stuff is I've been using, especially that first picture, since the very first year I taught, 2004, before you were born, and I didn't realize it was Martin Gardner who designed it. So this was like a big, like, wow, are you kidding me? I just figured this out today. I feel like it was like Kismet or something, but it was great. So I'm really excited because his artwork is amazing. So at any rate, Martin Gardner, have you guys heard of Escher? MC Escher? He's an artist. I'm sure you have seen some of his work. And then even just like logos. Like we got the logo for Starbucks, right? Does everybody know the mermaid logo? The green mermaid logo?
Yeah, Lily visits there.
I think she's a mermaid, isn't she?
Yes,
Okay.
she's a mermaid.
And then like even the McDonald's M. There's all sorts of logos that we look at that have beautiful symmetry, and then you can transform that logo to map onto itself, and there's congruency and similarity and this and that. But before we start with crazy things, we start with the easiest shapes on the planet, of course, triangles.
Right, Sophie?
Right.
That'd be easy to flip.
Lily's here.
So yeah, we work a lot with triangles in this unit only because it is the easiest shape with the smallest polygon, 3 sides. All right, so we're going to do rigid motions. We're going to discuss what that vocab word is, and today we're going to talk about and practice translations. Okay? Cool.
Okay.
So if you've never done this before, you got to make sure you're really, really focused. And if you have done this before, then it's a nice little reminder. All right. If you look at the front cover real quick, I kind of want to just break it down for you. The first kind of 3 days are learning like the different rigid transformations, and then we play a little bit more, and then we go into dilation, which makes shapes bigger or smaller, like your pupil dilates. And then there's some properties and sequences that we work on. There's constructions, a day of constructions at the end if it fits nicely. If not, we'll just skip it. I would presume with 10 days of instruction that we'll have 2 small quizzes and then a final unit test. Cool? Yeah. So you want to think about the quizzes as practice for your unit test, right? Because that makes how your quiz before was like that, ooh, I don't know some of that stuff and I need to learn it because it's already passed. Yeah.
Basically, we didn't have a test for
You did.
That's what we
That, so I use quiz and test interchangeably. It's just the test is kind of the end of the unit. My apologies. We haven't, so I'm hoping that if it's not tomorrow, then it has to be Thursday. But maybe I'll be able to do tomorrow. If I can get your grades in Infinite Campus, then we can discuss like how it all looks and why I don't really care what it's called. It's just your learning objectives. Okay, I know that sounds strange, but all right. So first of all, I just need you to turn to the back of the front cover because this is information that I was hoping everybody knew, but if not, it kind of just summarizes the basics of what a transformation is. Okay, so if you can turn to the back of the blue cover and follow along, you can highlight or underline as needed.
We're going to highlighter, guys.
That would be great. All right. So transformers, we're not like cars and trucks going into robots, but it's kind of the same idea, right? You're changing your shape.
Unfortunately, Sophia, there's no
Okay.
highlighters left.
My friends. Okay. So in reference to geometric transformations, it makes changes to the position, size, or shape of geometric figures. Typically, we're working with triangles, but we can work with any other shape. If you're talking while I'm talking, I'm assuming you cannot hear what I'm saying. Okay? So the deal is there's kind of 2 words that we work with. The figure that we start with is called the pre-image. Sometimes you will hear me just call it the original shape. So just be aware that I use those 2 words interchangeably. And then the after a transformation is called the image. And then we can do more than one transformation, and that's called, we can do a sequence of transformations, okay, to change a shape. All right, so there's some key principles that we'll be using as a theme throughout, okay? So the thing is there are, when we transform things, we do still have the same size and shape in the idea of angles, and then corresponding sides are proportional. So the only time we actually really change size is when we're dilating, right? Our pupil is getting bigger or smaller. So we have some more words at the bottom of this page that go through that. We have properties of shapes that are conserved, or sometimes we use the word preserved. So, like, you know how mummies are preserved? Egyptian mummies. Okay, so or like strawberry jam can be called preserves. It preserves the flavor. So when properties are preserved, it means those things don't change. So angle measure is preserved. Things like area does not change. So the thing is there's 3 transformations that preserve a lot of the stuff, but there's 1 transformation that does not. So we'll get to that. And then the deal is that we can represent these transformations with a couple different things. We're going to use coordinates on the coordinate plane most of the time. So we're going to be doing some graphing and this idea of mapping. So map each point of the pre-image onto the corresponding point in the transformed image. So it's the idea of you have a pre and a post, and they map onto each other like mirror images. All right, so now why am I talking about things being preserved and not everything being preserved is because there are these 3 that are called rigid motions. All right, so key vocab word for this unit, rigid motion. So out of our 4 transformations, there's 4 of them, 3 of them are rigid motions. So our rigid motions are translations, which is like doing just the slide. So to the left, to the right, okay? Translation, slide. There's reflection. Whoop, that should be a 2. There's reflection, and that's doing a flip. Okay, and you can flip over a line. And then there's a rotation, which is a spin. And the thing about rigid motions is they are the exact same shape and size when we're done. Okay, so these shapes, the image is congruent to the pre-image. Okay. So corresponding angles are congruent, corresponding sides are congruent. Life is good. And then the last one is not rigid. So our last transformation, number 4, is dilation. And dilation is when the size changes, but it still looks the same shape. It's not like it's been distorted. Okay, the scaling right triangle that's 3, 4, 5 is still a scaling right triangle, maybe 6, 8, 10. So dilation stretches or shrinks and this is where we use that we say the there's like it's still proportional. Whoops. And L. Okay, and we'll get more into that. So this front cover, literally, and I didn't want you to have to write down like a ton of definitions, but like this is like a quick reference, especially for the fact that 3 are rigid, 1 is not. 3 is rigid, 1 is not. How many are rigid? 3. And 1 is not. Okay, good. Great, turn the page. Okay. So today is translation. Okay. And we're going to practice it. We might do a little bit of the next lesson just because if we're going to talk about quizzing and all that tomorrow, then I want to have some extra time. But your homework will only be on translations. Okay? So, and I don't want to talk the whole time, blah, 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 but let's get through this in a nice way. Okay. So, translation. Translation is, it's going to be mapping the pre-image by sliding all points the same direction. Okay. So the key word is sliding, and then we'll talk about how we describe sliding. Okay, so if we look at these 2 shapes, and I know yours are not in color, the one over here is the pre-image. And it's called triangle ABC, right? So you put a triangle symbol in front to say that we're talking about a triangle. Triangle ABC. Now, the one that is the image, the after, is this one over here in blue. I'm just going to put down here, image. And how do I know it's the image? Because it has those little apostrophes, okay? So when we're writing the name of the shape, we say triangle, and we write A, but then we put an apostrophe on it and we say A prime. B with an apostrophe, B prime. C with an apostrophe, C prime. So we are going to map A, B, C onto A prime, B prime, C prime. Okay, so does that language make sense now? The little apostrophe is the word prime. Good? Okay. So knowing what you know about left, right, up, down, let's just go to point A. Point A is here right now. How do I get to A prime? So we've got to go up, and then we have to go where?
Left.
Okay, so there we go. I'm so glad. So we have to go up, and then which way are we going?
Left.
Left. Okay. So as smart as you and I all are, everybody gets left and right mixed up when we're doing these because we just get cuckoo. All right. So we are going to up and then to the left. So let's pause for a second. How many units up did we go?
We went up 3.
Up 3. And then how many to the left did we go?
5.
5. All right, so that's what A did. Did B do the same thing?
Yeah.
So if I go to B, did it also go up 3, left 5?
Yes, it did.
Okay. Do you have to say the up first? Could you have gone left 5 and then up 3?
Yes.
Yes. So all those words are 100% correct. Okay. So we use the vertices, the vertex. There's 3 of them, the 3 vertices to move the whole entire shape, and then we connect the 3 points. But every single point between B and C is being moved up 3, over 5. Left 5, left 5. And we have to be specific about our language. I just made the faux pas. The faux pas, you have to say that. So let's use this idea, and we're just going to focus on point A for just a second. Where is point A? What's its coordinate pair? So the original point A. So we go to the origin. How do you get to point A from the origin? 2, 3. Very good. Does everybody understand that answer? 2, 3 is where point A is. Where is A prime? What is A prime's location?
-3, 6.
Okay, so -3 up 6. Now I want you to think about this 3 and this 5 as operations, like adding and subtracting. So what did we do to the 2 to get to -3? -5, right? Does that make sense? -5. What did we do to the 3 to get to 6? 3 to get to 6. Up plus 3. And that's up 3. Okay?
That's cool.
So we can write a rule to explain the whole entire transformation, because the same thing happens with B and B prime. So let's just make sure we prove that to ourselves. Here's B. B is located at 2, -2. Right? So left 5 is -5. Up 3 is +3. Where should B prime be using arithmetic? Bless you. 2 subtract 5 is -3. -2 plus 3, we're out of the hole, +1. Is that where B prime is located?
Yeah.
Back 3 up 1. So our rule has to do with that. So we can write about translation using words and using, bless you, like a coordinate pair rule. So let's look at that. So it says details and rule. So for the details, we have to include direction and distance. So what we did up above, so here's our example. Up 3 units, and what did we do after that? Left 5 units. So directions are up, down, left, right. Don't use over, back. Those are the ones we tend to get goofy with for left and right. Okay, so that's one way to do it. Or with a rule, we take our original x, y coordinates, and then we're going to use the phrase mapping onto a lot. We just use a little arrow to say change all of the coordinates using this idea. So for this particular one, we did x, but was the x plus 3 or was the y plus 3?
The Y was supposed to
The y, what did we do to the x? Subtract, right? So x subtract 5. I can't write mine sideways. I'm running out of space. And y was plus 3. So remember that x's are going to get the left, right idea, while y is going to get the up and down idea. All right, so let's see if you just understand the rules that are down below here. So if you look at each one, they all start off with x comma y. All right. So this one says x plus 3. So x is left and right, just like our x-axis, right? X is left and right. So if x is plus 3, which direction are we going? Right. 3. And just putting right 3 is fine. And then what's y subtract 6 going to mean?
Down 6.
Down 6. Very good. Can you guys do the next one on your own? So x has to be left, right. Yep. Hey. Yeah, for sure. Okay. Who thinks they got B correct?
I do.
All right, add a line.
I said left 1 and then up 4.
Very good. Left 1, up 4. Cool. Okay. The next one just says X. So is it going to move to the left
No.
or the right?
No.
Right? It's not going to move left or right. What is the only thing that guy is going to do?
Stay
It's going to go. It's going to go down.
And then back up.
It's just going to go down 1.
Yeah.
Okay. Don't turn the page just yet. We have one more thing to kind of formalize before we turn the page. Sorry, I think the bottom of the page is there. Yep. Okay. Hang on. So we had to go down 1. I'm going to back out just for a second and kind of just go back up to the top. So we have triangle ABC, and we have triangle A prime, B prime, C prime, and all we did was up and over, right? I say up and over, and that's bad. I should say up 3 units, left 5 units. We did a sliding or a translation. So that's what translation is. Translation is the slide. And I know it sounds a lot like transformation, but the formation is like a generic and under the umbrella way of translation. So the only way, one of the ways that I try to remember that definition is if I slide from Rochester, New York to Quebec, Canada, I might have to translate from English to French. Okay? So if I'm sliding from country to country, I might need to change which language I'm using. Does that kind of make sense to everybody? Okay, so now last thing. Is translation a rigid motion? Did it stay the same size?
Yes.
Did it stay the same shape?
Yeah.
Yes. So here we go. This is a frequent flyer question on the Regents exam. So what's the best way to say that so we maximize our points, and this includes our quizzes. So is translation a rigid motion?
Yes.
Yes. Translation is a rigid motion because
It stays the same shape.
so we have to talk about same shape and same size. So I want to make sure we like just use some common language. So you can say because size and shape are the same, but that's kind of more a little bit younger. I prefer for us to get to because hang on, because corresponding. So I'm just going to put corresponding. Why am I not sponding? Corresponding angles and sides are congruent. So you're taking it up to geometry level language because corresponding, which means relative matching position, angles and sides are congruent. Is that hot in here or is it just me? I'm chill. Okay, I'm gonna just put this fan towards me then. I might just be more. Okay. I think at this point then we can turn the page. All right, so Jade, you know that the notes are also on the one that's online, right? Okay. So I'm gonna go ahead and turn the page and then we'll see some of this again on the next page because this is still translating. Okay. So here we go. We're going to analyze one and we're going to go through lots of the parts and pieces. So here you go. Given the translation to the right, here it is. Take a moment, examine it. So when you're examining, which one is the pre-image? Where do we start?
The one that doesn't have a prime.
Yeah, and where do we end? Yeah, so I will often put this on my paper. Start and finish or end. There's nothing wrong with marking my picture with words that are going to help me so I don't screw up my left and my right. Okay, so now can you guys describe that?
Yes, we may.
Okay, so describe the translation. So you would say translate. And now you're going to use direction and distance. And I would probably use point C to figure it out because it's the one that's farthest to the right. It's kind of leading the shape. Because any set of corresponding points will work. And then we have to be able to count on grid. And so I just kind of want to check. See if you can figure out how many units to the right, how many units to down. If you didn't get the number 6, just let me know and I can come help you. 6, good. Okay, yes.
Does it matter if you put like the number before the word? Like write 6 or like.
No, it doesn't. So if I'm gonna put the number in front, 6 right. Yeah, that's sometimes I say 6 units right or right 6.
Does it matter which one I put first?
It does, and it doesn't matter if you do left, right first or up, down first.
Okay.
So right 6 and then what? Down 3. So where does it make where order matters is when we do the rule, right? X comma Y. So you always put the starter, because that's the pre-image, right? Then you put an arrow, and then what's going to happen to every X coordinate is that plus 6. Very good. And then what's going to happen to every Y coordinate?
-3.
Very good. So Y subtract 3. And then you can always check it. All right. So there's a new property that we need to talk about. Like, properties are angle measures. Properties are slope. Properties are lengths of segments, area, perimeter. This new one is called orientation of the letters around the shape. Okay? So orientation will help us determine which transformation is which. So I'm just going to kind of just draw a little sketch here of what we have right now. So if I look at this one, A, B, C, and I am naming the triangle ABC. And I'll let you catch up if you want to write it down. It's up to you. When I talk about the orientation of the letters, I'm talking about the fact that to name the shape, it's going around clockwise. Do you see that? A, B, C, A, B, C, A, B, C, right? So I'm just going to put a CW in this one. So you see, and then sometimes I'll do this on my shape for kids to help me understand it, okay? Orientation is how we name the shape going around the shape. So when I go over to the image, does the naming of the shape stay the same in clockwise? A, B, C, A, B, C, A, B, C. So because this is also clockwise, we can say that the orientation stays the same. Orientation stays the same. It is conserved or preserved. And that's not true for every transformation. Translation is the simplest one, right? All we're doing is sliding that guy around. It's not really exciting. But it is where we start with our analysis because it is simple. Okay, so translation preserves orientation. All right, so now let's find slope. So what do you guys know about slope?
Y equals mx plus b.
Okay, so when we say y equals mx plus b, slope is the letter m in that.
Yeah.
Okay, so let's connect the dots then. I'm just going to go over here. Y equals mx plus b. So if I have the equation of the line, m is a number, right? And it's the slope. And it's a value or number that describes steepness of a line. And this is something we still use in this class as well. Not all the time, but it reoccurs throughout the year. So when you are on a graph, a lot of times when I'm talking about slope, I like to use the phrase slope equals rise over run. Do you guys use that one?
I've heard that.
Yeah, okay, rise over run. So the thing about rising and running, especially the running, you always want to go from left to right when you run. So running is always going to be in this direction from left to right, and that way you get the nature of positive or negative slope is usually easier or more accurate when you do that. So it wants us to play with the slopes of A, B, and A prime, B prime. All right, so let's go back up to our picture. Oh, there's AB. So once again, I'm just going to mention left to right. So if I were to start at the left, which point am I going to hit first, B or A? B. So I'm going to start at B. Okay, so when I'm at B, that's red already on my screen, and I'm at B, and I'm doing rise, I'm not really rising, am I? I'm going to fall, right? So B, I fall, and then I run. So how far did I fall? 2. So that's -2. How far did I run? 1. Okay. And then same thing is true here. So working from left to right, I hit the B prime first. I'm not rising, I am falling 2, and I run 1. So I'm going to scroll and summarize down in the area. Okay. So for the slope, I'm going to make a little table here. Okay, so for AB, my slope was down 2 over 1. And can we simplify that to just be -2? Yep. And then for A prime, B prime, and I'm forgetting the hat on it just because I don't have enough room, and that's okay. So the slope was the same exact thing, right? And I can blow this up. -2 over 1 equals -2. Okay. Just give me a little thumbs up when you have that written down, because I want to make sure people have it before I scroll and then go bonkers. I'm going to go bonkers. One person's still writing. Okay. So I'm going to go. So it's asking, what does this mean about the segments? Well, they have the same slope, right? But there's something bigger than that I need to show you on the picture. They have the same slope. I'm going to scroll. I'll scroll back. And then hopefully I can do this without... I'm going to make a mess of my picture. Don't do this on yours. I'm going to try to do this and that. And maybe I'll use this. I think this will work. Okay, so ready? I'm going to go like this. And then this is really what it takes. So I extended those lines so I could see what about the two segments. They're parallel. They're parallel. Very good. They are parallel because they have the same slope. That's a big idea. Have you guys ever known that? No? See, now you know. Okay, so we go back down here to summarize it. So they have the same slope, which means they are parallel. So that means we can write AB is parallel to, so this is our symbolic language, right? A prime, B prime. And you guys have been writing a lot, so I'm just going to say it out loud. You don't have to write it down. Parallelism is a property that was preserved. So go back to your strawberry jam. Still tastes like strawberry jam, right? The corresponding sides are still going to remain parallel because when you slide, it doesn't turn it, right? So guess when we don't have parallelism preserved? Like when we rotate, right? Because I take a triangle that goes like this and I flop it over like that. Parallelism is not preserved. Okay, but this time it is. Yay! So this is a preserved property. So let me just back out, and I think we're going to stop here today, but let me just back out real quick and make sure I'm happy with that. Okay, so we learned how to, what was the goal of the lesson? Translating, sliding. So my friends that are ninth graders, is this the first time you've seen this, like, formally? Hey, Josh, do you remember this at all? No, a little bit. So for some, did you ever see this before in like seventh or a little bit? Okay, I don't know if you did it in seventh or in eighth or like, because we're doing algebra 1 in eighth, right? So it's possibly I would have shown it to you at the end of seventh. So you have learned that translation is one of how many transformations? 4. Great. This is the most basic one. All it does is slide. You can describe with words or you can describe with a rule. And we're going to start talking about the fact that properties are preserved, like orientation and parallelism. Okay? I'm going to pass out your homework. It's an easy front and back. Okay?
Perfect.
Perfect. Yeah.